One problem with our simple comparators is that the op-amp is not ideal. Specifically, the gain is not infinite. Typically, the open-loop gain is only on the order of 100,000. And that's, of course, the way these op-amps are connected because there's no feedback. There is no loop. That means that there is a finite yet small range of voltages around the transition point where the op-amp will actually behave as an amplifier, not as a comparator. So this could get to be a real problem, possibly if you had a really slowly changing input signal, because you might not get a clean, almost instantaneous transition from low to high and vice versa. If that input signal's changing really, really slowly as it goes through that transition point, it ends up being in that amplification region for some finite amount of time. That may or may not be a problem. Potentially more of a problem is noise. Let's say that you wanted to build some sort of a frequency counter. Now, typically what you do with a frequency counter is you take your input signal, whatever that happens to be. Now, in the simplest case, you've got a nice, clean, periodic signal, like a sine wave or a triangle wave or something like that. If the signal gets really complicated, doing a frequency count can get to be very challenging. So let's take the sinusoid as a simple example of this. Here's a sinusoid. If you simply run this into a comparator, you will get a square wave out. I've changed the level of that square wave so it easily fits on the same scale with our simple little sine wave. It would probably be at the power supply levels. But nonetheless, that is a nice clean pulse signal, and that is easy for a computer to do something with. The sine wave's a little bit harder for the computer to do something with. So you usually need to clean those signals up, get nice clean pulse type signals, and then the computer can simply basically count the pulses. However many pulses there are per second, that's the frequency of the signal. The problem is all signals have noise. Let's look at a sinusoid that has some noise added to it. Alright, there is an example of a sine with some random noise added to it. The problem is this, and the higher the noise level, the worse this problem gets. As that sinusoid crosses through the comparison point, which I have set in this example to be at 0, the noise may actually cause the comparator to switch more than one time if the noise causes it to sort of bounce up and down around 0 as it goes through 0. So if we look at what the comparator does in this case, note we get a nice clean transition going down, but we get an extra spurious pulse when it goes back up because of the noise. If we do this again with a different noise signal applied, in this case, it did it right. It did not have any extra transitions at the 2 0 crossings. If we do it again, now we picked up an extra one on the falling edge. If we do it again, now we have an extra one on the falling edge again. And again, oh, look at this. Now we've got an extra one on the falling edge and an extra one on the rising edge. If we keep going, note there is no consistency. There's 2 and 2. Oh, there's 2 and 3. Now, if your noise level were to increase, then you're going to tend to get more of these false pulses. You actually, depending on the parameters of the problem, could deal with this in software if you were using a computer to count these pulses. That's not that difficult to do within certain limitations. But it's actually quite easy to avoid this problem in the first place, so that you send a nice clean pulse to your computer to be counted. In our next video, we are going to talk about Otto Schmidt and his work with the nervous system of squids. Believe it or not.